Hey, Science Nines, it's Manchak here with your, can you believe it, very last video lesson for Science 9. We have done the better part of 2.5 units together in this sort of online environment that we've been working through, and I am so incredibly impressed by how all of you have managed to figure this out and work your way through it. So well done for all of you. So I'm going to make this as quick as we can. Now, concept E4 is going to be relatively long, and then I'm going to tack concept E5 onto the end of that when we're done, just so you guys are aware that that it's going to be a bit of a longer video this week. But hey, it's your last one, and then you're done. So hey, that's pretty cool. So I wanted to just talk with you guys about where we've been and where we're going, so that we are aware of what's going on. So this is our last couple of concepts in Unit E. Like I said, E4 is going to be a bit longer. E5 I'll do relatively quickly for you, so it won't be too bad. Where have we been? Well, we've talked about some early views about space and some information about the technologies we've used to examine space and about the matter that we find out in space. We've talked about our solar neighborhood and how to find the position of objects in space. We talked last week about space transport, living in space, and applications to Earth. So what's it like to be up in space? What are the challenges associated with that? All sorts of things like that. This week, what we're going to do is we're going to look at E4, which is technology seeing and interpreting space. So we're going to look at different kinds of telescopes and imaging devices that allow us to see up into the stars and what's out there, and for us to understand a little bit more about what's going on up in our universe. And then, like I said, E5, we're going to try to tie everything together, talking about space, society, and the environment, okay, and tying a little bits of pieces together. And we're going to talk a lot about, or a fair bit about, Canadian contributions to what we know about space and what's going on. So, as always, this information that is down here on this page, you can find by just looking up above where this video was found. So you can track this information down very easily. It says I'm Galileo. And textbook pages are listed here as well. I've included 4 videos for you on this playlist for this lesson. Videos, a couple of them are a little long, but they give you some information about telescopes, those kinds of things that I think you might find interesting. And then something from Commander Hadfield again about, I think he's Colonel Hadfield now, actually, about the Canadarm, which is a concept E5 sort of thing. There'll be some practice questions you can work on, as well as worksheet number 3. You can wrap up concept E4 on worksheet number 3. There'll be a practice quiz, as always. Please wait for feedback before you move on to the summative quiz. So I think with that, keeping it relatively short, I'm going to drag this out of the way, and we're going to get started with the actual lesson part. So please make sure you've got your notes out in front of you and you are ready to work your way through this lesson with me. So first things we're going to do is concept E4, which we're going to be talking about ways that we can view things in space and how we know about those things in space using telescopes and various other creatures. So it's funny that I threw this meme up there because, well, Galileo was one of the ones that we sort of used as a father of trying to sort of see what's out in space. So telescopes are the big thing we're going to be talking about in E4 and what we can do with those telescopes. And they allow us to see objects that are very distant in space. Now, if you think back to Science 8, in the light and optics unit, we did talk a little bit about telescopes and light back there. And this is a nice way to sort of think back to what we did last year and examine what's going on from the perspective of space in this case. So in 1608, Hans Lippershey made one of the very first telescopes, but it was actually Galileo, and you guys learned about him last year in science and probably in social studies when you covered the Renaissance, who made a practical use of the telescope. Now, optical telescopes are basically light collectors. Light comes into the end of the telescope and gets collected and then shone into our eyes, or even maybe for some of the more modern telescopes, the more advanced telescopes, they get shone onto some sort of a a computer device like a CCD that allows the telescope to capture what's going on in space instead of our naked eye. We're collecting it in a digital format, I guess is what I'm trying to say. And they gather light and they focus it to create a magnified image. They basically are trying to bring something that's really far away closer to us. There's a series of lenses or mirrors that enable the optical device to collect and focus light from stars. And there's two basic types of simple and maybe even more complex telescopes that we talked about last year, and I'll refresh your memories on this year. These are refracting and reflecting. And you should be thinking back to last year when you covered light and optical system stuff. Refraction is referring to the bending of light, and reflection is referring to light bouncing off of something. Okay, and laws of reflection and refraction were associated with that. So the first thing is a refracting telescope. A refracting telescope uses lenses. Okay, this is the important bit. It uses lenses to gather and focus light. So a simple refracting telescope is going to have two lenses, one at the very end of the telescope and one close to the eye. And what this one is doing is gathering the light, and then what this one is doing is refocusing it so that it appears to be a focused image on our eyes. The thing about refracting telescopes is that we're limited by the size of the lens that we can create. Right? A simple refracting telescope for you or I to use for home use is, maybe about 3 or 4 feet long, and we can easily set it up on a tripod and look up into space. If you want to look at really far stuff in space with a lot of detail, you're going to need a really big lens. And we've created those really big lenses, but it's hard because if the lenses have any imperfections in them, or if they aren't curved the way they should be, or the glass isn't as clear as it could be, we end up with issues with the image that we're creating. So that's something to consider with these refracting telescopes, is it's kind of tricky to make super big lenses. Okay. The next kind of telescope we talked about was a reflecting telescope, and these ones use mirrors. So refracting lenses, reflecting mirrors, because mirrors reflect an image, right? So reflecting telescopes use mirrors instead of lenses to gather and focus the light. Basically, a process called spin casting makes today's mirrors by pouring molten glass into a spinning mold, and it sort of spreads itself out. And our mirrors need to be curved. At least one of the mirrors needs to be curved, and we can sort of see that if we look at this diagram here. Here's a curved mirror down at the bottom. Whoops. And that curved mirror is meant to take the light, gather it, and then reflect it to another small mirror, which then reflects it up to an eyepiece. So the best way to tell the difference between a refracting and a reflecting telescope, and I think we talked about this last year, is a refracting telescope, you tend to look at the end, like you might, something along those lines, where I'm looking through this end over here, and the light is being gathered closer to the camera there. In a reflecting telescope, you're going to be, the telescope will be running this way, and there'll be a little eyepiece on it that you'll be looking down into, and light will be gathered over here, and there'll be a mirror then reflecting up to my eye to see the light that's being gathered over here. The glass is forced to the edges, cooled and solidified in the spin casting of mirrors, and we can make mirrors as large as 6 meters across, maybe even larger now, which is pretty impressive. That means, so why do we want a bigger telescope? Why do we want to make a massive lens or a massive mirror? Well, the bigger it is, the more light we can gather. The more light we can gather, the more we can see things way out in space, the more information we can get with what we're seeing. If we can't gather enough light, we can't see stuff clearly or can't see it at all. But the more light we can gather, the more clearly we can see an object, and the more distant an object we would be able to see. Okay, so bigger means better in this case, as long as it's created properly. There's also other telescopes out there that we've started to play around with over the last, let's say, 20 or 30 years, instead of just having one massive mirror, what if we piece together a whole bunch of smaller mirrors and make something even bigger? So what you're seeing at the bottom here are some large optical telescopes that we're using. So we had a 4.2 meter telescope, we made a 5 meter telescope, we made a 6 meter telescope, we made an 8 meter telescope. With these particular lens or mirrors, but now we can start to piece together a whole bunch of mirrors and capture information on each of those mirrors and reflect it into one spot and get an image that is even clearer and crisper than what we had before. So what we call our segmented mirror telescopes, using these smaller segments to build one larger mirror. And it results in a large telescope with enormous light gathering ability and resolving power. Resolving power is what I'm talking about, is that clearness, that crispness of the image, the ability to distinguish details in an object. This is resolution is what we're talking about. If you have low resolution, it's hard to tell the difference between two things that are really close together. If you have high resolution, you can really clearly see the difference between two things that are close together. Okay, so we've talked about refracting and reflecting telescopes. We've talked about segmented mirrors that make bigger reflecting telescopes. Let's have a look at what we call interferometry. Okay, this is a fun word. It's the technique of using a number of telescopes in combination to create a much larger, clearer image. So when working together, these telescopes can detect objects in space with better clarity at greater distances than any Earth-based observatory. The Keck-1 and Keck-2, and they're pictured here on this image, as well as are 85 meters apart from each other, but when they work together, they can detect objects in space with better clarity than any other Earth-based observatory. So these are Keck-1 and Keck-2 that are found at the Canadian French Hawaiian Observatory in Mauna Kea, Hawaii, and they operate with 3.6 meter mirrors, and they're gathering. They're both gathering light. They're both pointed at the same spot, and then we're taking those two images and merging them together to try to get a much clearer image of space. Why do we do this? Because, like I said in the last slide here, we can get better clarity, and we can see things that are much further out in space than we do right now with our more simple telescopes, if you want to call them that. I wanted to talk just a little bit with you about the Hubble Space Telescope, because there's a lot going on with this telescope. One of the problems with observing space from Earth is that we have an atmosphere in between us and space. And in the atmosphere, light can get scattered a little bit and make it more difficult for us to see things clearly out in space. So one of the things that was done is we built and launched in 1990 something called the Hubble Space Telescope. And it basically orbited the Earth for a number of years. And it was a cylindrical reflecting telescope, 13 meters long with a diameter of 4.3 meters. And it got outside of the atmosphere and allowed us to see things even more clearly than we would here on Earth, maybe even with a bigger telescope. And that's because it got outside of the atmosphere. So Hubble Space Telescope orbited around the Earth, and it collected images from all over in space. And I believe what happened is when it got near the end of its life, they fired the thrusters on it and sent it out into space even further. And then it started to gather images as it moved its way through the solar system and out past the solar system, where it eventually disappeared off of our ability to track it anymore. So that's really cool. And the images that were gathered from the Hubble Space Telescope are amazing, which just gave me an idea. I will add a video to your playlist for this week if you want to watch it, on just some of the images that the Hubble Space Telescope was able to grab. So yeah, just a little bit on a particular type of telescope. So moving away from more conventional telescopes, what we're going to move into is talking about sort of some of the newer telescopes that are out there, and telescopes that allow us to view stuff outside of the visible spectrum And this requires us to go back and think a little bit about what we learned in Science 8 about light. We know that light exists on what we call the electromagnetic spectrum, which is a range of wavelengths that includes the longest wavelengths of radio and television signals, and we get shorter wavelengths as we move down here. Oops, come back here. Visible light exists right here in the middle, and then that is only a very narrow section of the electromagnetic spectrum that we're able to see with our eyes and interpret with our eyes. But stars and other celestial bodies release a whole bunch of other kinds of light or electromagnetic radiation that allows us to that we could capture and learn more about the things that we're seeing up in space. So I'm not going to spend a ton of time talking about this with you, but there is a short video I included in the playlist, 2 minutes long, just running through the electromagnetic spectrum again with you. This is the spectrum itself, where the longer wavelengths are over here and the shorter wavelengths are over here. If you remember from last year, longer wavelength means lower frequency. Shorter wavelength means higher frequency. Frequency is the number of waves that pass a given point every second, which is what we talked about here. So all of this light, as we call it, whether it's visible or whether it's outside of the visible spectrum, travels at the speed of light and has different wavelengths and frequencies. They're all a form of energy. Remember, a wavelength is a distance from one point to the same point on the next wave, and frequency is the number of waves that pass a single point in a second. Energy with short wavelength has high frequency. Energy with a long wavelength has low frequency. Remember those from last year. Gamma rays are the most dangerous, and radio waves tend to be the safest. Gamma rays are the most dangerous because they have the shortest wavelength, highest frequency, which means they are the most energetic. They carry the most energy per photon of light in that case. Visible light is measured in micrometers, with 1 micrometer equal to about 1/1,000,000th of a meter. So we're talking about very small things. Wavelength, okay? So just to remind you, a wavelength is from one crest to another, or it could be from one trough to another on the next one, okay? And then frequency has to do with how many things pass per second. So if we see from here to here is 1 second, from here to here is 1 second, then we've got a higher frequency here. There's more of these waves that are passing in that 1 second than there is here, okay? So that is how we talk about frequency and wavelengths of light. That's a really quick review because I want to get into talking about some new stuff with you here. So these these optical telescopes that we've talked about before, the refracting and reflecting telescopes, are great, but they're really only showing us stuff on the visible spectrum, or at least they were initially. Now we've developed other kinds of technologies that allow us to capture other parts of the electromagnetic spectrum, and allow us to see different things out there than what our naked eye would be allowing us to see. So as we use radio waves to try to capture what's out in space, we're starting to discover that certain things like stars, galaxies, nebulas, even the sun and some planets are releasing radio waves in some way, which allows us another form of electromagnetic radiation to look at these celestial bodies and figure out what's going on. So these radio telescopes have allowed astronomers to have an advantage over telescopes because they're not affected by weather, clouds, temperature, or pollution. So they can be operated day and night, and they're not being affected by what goes on in our atmosphere. So again, that's great. Great for us. Much of the information that has been gained about the composition and distribution of matter in space, namely of hydrogen, which makes up a large portion of matter in our Milky Way galaxy, has come from our ability to look at these things with radio telescopes. So it's how we learned, for example, that the shape of our galaxy is actually a spiral. So we are in a spiral galaxy. Radio telescopes are made of metal mesh and resemble a satellite dish, but are much larger and are curved inward. So they're a concave design with a receiver in the center. That receiver then takes the information that is being collected by the big satellite, or the big radio telescope, and it digitizes it and turns it into something that we can interpret later on. So this is what one of the large radio telescopes might look like. So it's collecting, basically it's detecting, the radio waves here, and then all of those radio waves are reflected to a receiver, and that receiver is then gathering that information and digitizing it in some way for us to see it. At this point, I just wanted to mention there are two videos in the playlist at the very beginning that talk about telescopes. Telescopes initially, which is the longer one, and then one more about the telescopes that we have today. So a little more of a historical one, and then one that is talking about more of the modern telescopes we have. We can also hook our radio telescopes up in combination to do radio interferometry as well. And we can combine several small radio telescopes, just as we would with an optical telescope, to get a greater resolving power as well. This improves accuracy and performance of the image that is making these radio maps of the piece of space that we're looking at. We would call one of these things an array. And so, for example, the Very Large Array in Sirocco, New Mexico uses 27 telescopes arranged in a Y shape, and we can see part of it here, to improve the accuracy. So, first off, Very Large Array. Gotta love astronomers for making names like that. I think it's really cool. And there's something else I was going to say, and I completely forgot about it. But we can get these arrays. We can point all of those radio telescopes at one piece of space, and then use all of them to gather different bits of data, which gives us more complete picture of what's going on out in space. Okay, so viewing more than the eye is what we're doing here. So just a couple of things I wanted to mention to you guys about this, because we know that our eye can only see in that visible range, that very narrow part of the electromagnetic spectrum. But there's so much outside of that. There's radio waves and microwaves and infrared radiation. And then on the other side, there's ultraviolet and X-rays and gamma rays. All of that stuff's out there, but we can't see it. So we're developing more and more technology to allow us to see what's out there. For example, ultraviolet radiation is absorbed by the atmosphere and can't be studied very well from Earth. So we would need something out of our atmosphere in order for us to see anything that might be emitting ultraviolet radiation. A distant planet orbiting a distant star cannot be seen because of the bright light from its star. However, when viewed in the infrared spectrum through a radio telescope, the star's brightness dims as the planet's brightness peaks. So what we can do is start to detect planets orbiting around other stars, either by detecting radio waves coming off of them, or as that planet passes in front of the star dims just a little tiny bit. And how much it dims depends on how much or how big the thing is passing in front of it. We can find telescopes that way. So the Keck Observatory that we talked about before in Hawaii is actively searching for planets with its radio telescope. Other discoveries that we've been able to do with these radio telescopes and other more advanced telescopes is we've been able to measure fluctuations, changes in microwave energy left over from the formation of the universe, which has allowed us to get a little bit of a glimpse into what things were like, billions of years ago, just after the universe was formed. We've been able to detect X-rays emitted from black holes and pulsating stars, which tells us a little bit about what those celestial structures are all about. And we've been able to detect huge bursts of gamma rays appearing without warning and then fading just as quickly. All of these things are telling us more about what's going on in space. We've been able to send space probes up, and we talked about probes in the last lesson. These are unmanned space vehicles that go up into space to explore the distant areas of our solar system and even look out beyond our solar system. So we know they're unmanned satellites or remote controlled landers that put equipment on or close to planets where no humans gone before. We've sent probes to Mars to do some remote sensing on Mercury and Jupiter as well. We've taken soil samples on Mars, we've landed on Venus, and we've studied Saturn rings. Page 444 of your textbook has got lots of good details on that. The most recent probes to explore Mars are still there. Spirit and Opportunity are still there, and they're looking for evidence of water to determine if Mars at one time could have supported life. And that is one of the suppositions out there. The only place that has been explored physically by humans is the moon. Apollo 11 was the first landing, and there have been others since then. And I'm sure that there will likely be others in your lifetime as well, would be my guess. The next thing that's been talked about is trying to establish a base on Mars for interplanetary missions and those kinds of things. But that's something that may happen in your lifetime, but it's sort of out there still. Okay, I wanted to talk next here about how we use some technology to interpret what's going on in space. This stuff is a little bit tricky, so do your best to try to understand it, and if I need to, after my explanation, I may find a couple of videos for you guys to work on. Really, I want you guys to know these things just on a general level. It's basically how we're using technology to figure out what's going on up in space. So things like the distances between stars or bodies in space, what stars are made up of, and what a star's direction of motion is. And we'll talk about those quickly. So triangulation and parallax are two ways to measure distances indirectly on the ground or in space. So distances we're talking about between two things. Triangulation is based on the geometry of a triangle. Weird. Triangulation, triangle, strange. Okay. By measuring angles between the baseline and the target object, you can determine the distance to that object. To measure the distance indirectly, you need to know the length of one side of the triangle and the size of the angles when creating imaginary lines to draw from the base of the object. So here's our distant object. We're going to use triangles to sort of show this out. So if we are standing anywhere along this line here, and we want to figure out where point 3 is, how far away it is, we could sort of stand over here and measure the angle, and then move over here and measure the angle, and then we have a distance along here, a side of that triangle that we know. Then we can use some trigonometry to sort out what's going on. Complicated. I don't want to get too deep into it. I want you to understand that triangulation requires the use of triangles to try to measure the distance between one object and another. So if you wanted to do this, you would follow these steps, and we're not going to do this. We might have done this if we were live in class, but on a flat area, you'd measure off an accurate baseline and mark each end of the line so you can identify it easily. Then you'd select an object to be your viewing target at a distance. Then standing at one end of the baseline, you're going to use a protractor to determine the angle between your sight line to the object and the spot on the baseline where you were standing. Okay. Then you stand on the other end of the baseline again, and you determine the angle from there. Then you make a scale drawing of the triangle using the length of the baseline and the two angles. And then on your drawing, you mark a perpendicular line, measure the line, blah, blah, blah. So this is sort of what you would be doing here, is you would know this distance between here and here. You would have your distant object over here. Then you would measure the angle, from you basically measure your 90 degrees from here to here, and then you'd measure how far off the baseline you would be finding that distant object. You'd go over here, figure out the angle to find that, basically the telescopic sight line, and then you would be able to draw a 90-degree angle in here, and now you've got two right triangles with an angle. We would be able to use some trigonometry to figure out then what this distance is here. We could also figure out what this distance is here. Okay. Parallax is something different. Okay. Parallax is the apparent shift in position of a nearby object when the object is viewed from two different places. Okay. And that has to do, you can sort of do this by closing your eyes and sort of holding your finger up in front of your eyes. And if you alternate, this probably looks really funny. If you alternate closing your eyes, you can see that your finger appears to shift. That's due to parallax. And we can make measurements based on that. So astronomers use a star's parallax to determine what angles to use when they triangulate the star's distance from Earth. The larger the baseline, the more accurate the result. So the longest baseline that astronomers can use is the diameter of the Earth's orbit. Remember, the distance between the Earth and the Sun is 1 astronomical unit. So the Earth's diameter of the Earth's orbit is 2 astronomical units, if you want to think of it that way. The measurements have been broken into 6 months apart to achieve the diameter of the orbit. So if we can observe the nearby star over here, and then observe it over here, then we can determine the parallax between the two observations, and that would allow us to determine something off in the distance. I think I'm going to find a video to help you guys with this. Okay, so that's triangulation and parallax. Astronomers also can determine stars' composition based off of the light that refracts from different stars. Okay, so the stars have dark bands and distinct sequences and thicknesses on their spectra when we view them with maybe a radio telescope, something along those lines. So that means that those dark bands that we have are kind of like a fingerprint for each element that we have out there in space. The spectra of the star is then compared to the known spectra of elements to determine the star's composition. And we use what's called a spectrometer to determine that. So this is what I'm talking about here. And this video will be in your playlist as well. So normally each star has a unique spectrum, what we call a spectral class. For example, a hot star has a spectrum rich in hydrogen lines, whereas a cool star has thicker lines from the metals that are going to be in it. And so a spectrum binary is when you cannot see two stars in the sky, but a spectrum of an object to show two different stellar classes below. Creates a spectrum binary. And it's these patterns of these dark lines on here that tell us what those stars are made up of. I'll include this video for you guys in your playlist so you can have a quick look at that. The last thing we're going to talk about in this section is determining a star's direction of motion. In other words, is it moving away from us or towards us? And that's the best that we can get from this. What we know about Doppler effect, you may not have been introduced to this before, is we first discovered it with respect to sound, but we also have found that it can be emitted with light as well. In sound, we get a change in the frequency of sound waves, the pitch of sound waves, because they're stretched or squeezed depending if an object is moving closer to you or whether it's moving away from you. So if you think of an ambulance, for example, an ambulance that's coming towards you and then moving away from you kind of has a different sound. I was going to imitate it here, but I have to think about it for a second. And instead of me, sitting there and doing an awkward pause, I'm just going to pause and think about it for a second. Instead of an ambulance, I was just thinking about this. Instead of an ambulance, think about standing on a highway, or not on a highway. Sorry, don't stand on a highway. Think about standing beside a highway and waiting for a car to go by. Okay, what's going to end up happening, and I think you guys have observed this before, is as the noisy car comes towards you and then goes away from you, you kind of hear this. So I started out high, because what's happening is the car's moving towards you, the waves of light are compressing into a shorter frequency, so higher pitched frequency. And then as the car passes you, it got lower. Right, and that what happens is the waves of sound are stretching into lower frequency sound. So high frequency is that high pitch kind of sound, and that is shorter wavelengths. And then low frequency is that lower register of sound, and those are longer wavelengths. So that that goes by is the high pitched, means those waves are compressing into a higher frequency. That low pitched is the waves are lengthening into a lower frequency. Light does the same thing. If you remember, our light spectrum goes from red, orange, yellow, green, blue, indigo, violet. And so I kind of think of it as a blue and a red end, so to speak. The red end are the long wavelengths, low frequency, and the blue end or the violet end is the shorter wavelength, higher frequency light. What happens is if a star is moving towards us, then we're going to find that the light should appear a little bit bluer from that star. But if the star is moving away from us, it should appear a little bit redder. So here's how this works. The position of the dark bands is what shifts when the light waves of a moving star. This is the important bit here. The spectrum of an approaching star shows how the dark bands shows the dark band shifting to the blue end of the spectrum if it's approaching, because those light waves are shortening, becoming higher frequency. Whereas the shift is to the red part of the spectrum if the star is moving away. Those light waves are stretching. Okay. The amount of shift indicates the speed at which the star is approaching or moving away. So if we wanted to look at it this way, if we've got, you know, the what's going on over here, if we look at the train that is moving towards this individual, the light is going to shift more towards the blue-violet end of the spectrum, or if it's moving away from this individual, it's going to shift more to the red end. So we call it a blue shift versus a red shift. Blue shift means it's moving towards you. Red shift means it's moving away from you. Okay. And then I'll include this this video in here as well into your playlist that shows a little bit about what's going on with Doppler effect, is what this is called, and that allows us to detect what's going on with objects moving to or from us. All right. How do we apply this Doppler effect stuff that we figured out? Well, we actually use radar detectors, radar guns, which send out a signal to and receive one back from the vehicle. And how much it's shifted in the time that it was sent out and received tells us how quickly that vehicle is going. So our radar gun sends out a signal, and we've got these outgoing waves, and then how quickly they come back, or they're going to come back at a certain speed, but how much they've shifted towards the blue end of the spectrum tells us how much or how quickly that object is done. So the radar gun does this calculation for us. We've done all the testing, and then it does the calculation for us. All right, so that is the end of concept E4. I know this video is stretching quite a bit here, but I want to really quickly run you through E5 and be done with the course at this point. So if you wanted to hit pause right now and work on the E4 section, I believe it's questions 7 through 12, if I'm not mistaken. I might have that wrong. On the worksheet, you're more than welcome to go and do that right now and then come back to me later on. Or if you want to continue on, then we will continue on to section 4, which is all about how we've been affected by space exploration and the development of technologies. So I'm going to really quickly hammer through this because a lot of this we've talked about so far. We know that there are risks and dangers associated with space exploration, right? Accidents have a loss of life, which is tragic, like the Challenger explosion in 1986, or the Apollo 1 astronauts dying during a training exercise, or the Space Shuttle Columbia explosion when it broke apart on re-entry. And all of these things have setbacks that cause problems, and there's tragedies, and these things this is one of the dangers, is that this isn't a tried and true method of stuff. We're still learning as things go by. I think there was a big failure of one of the rockets that tried to launch last week, or they're doing a test of a rocket last week, and they're going to learn from that stuff, and hopefully it's not going to have loss of life involved in it, those kinds of things. Manned space travel has a whole bunch of dangers, and we've talked about these already, but I'll just quickly talk them through. A launch can be affected by many dangers, including the fact that we have highly explosive fuel attached to a big long cylinder that you're firing up into space. There could be poor weather that we didn't anticipate. There could be a malfunctioning piece of equipment that we're not sure. Human error comes into play, and even birds can cause problems if they're unexpected or they fly into a spacecraft when we don't want them to. Once in flight, the spacecraft can be affected by a whole bunch of other things. There's floating debris, there's meteoroids, there's electromagnetic radiation. All of these things we can and cannot predict depending on the situation, and we have to be prepared for. Re-entering the Earth's atmosphere has its dangers. If there is something even a little bit wrong with one of the space shuttles, like the Space Shuttle Columbia, we could end up with huge disasters happening. When you go from no atmosphere and no friction into an atmosphere that is chock full of air that is full of particles, you get tons of friction. It gets hot as you're coming in. And if there's something going wrong, it could be catastrophic at that point. Re-entry path the spacecraft takes must be perfect. Otherwise, if it's too shallow, it could actually just reflect itself off the atmosphere. If it's too steep, it could end up burning up with the extreme amounts of friction it's experiencing. Once we get into space, we have to watch out for space junk. Space junk is all of the stuff that we fired up into space that has fallen off of rockets or satellites or space shuttles or space stations that remain up there. And this can include even little tiny flecks of paint into large pieces like non-working satellites. And all of these are extremely dangerous to something that is moving in orbit or moving out into space. And these, even a little thing like a fleck of paint or a screw or a bolt, could be moving so quickly that a collision with some sort of a space vehicle could be catastrophic as well. Could punch a hole in it, something along those lines. So things we have to watch out for. Once we talk about the hazards of space, we know that there's been over 4,000 missions sent into space, and each have left behind little bits of debris. Some of these little things are called micrometeorites that are constantly bombarding the space station. Could be little flecks of paint, could be dust left over from a comet passing by, whatever it is. They travel at really, really high velocities and can cause a lot of damage. So we need to consider that as we build things out in space or put things out into space. And once they enter the atmosphere, they usually burn up. See, the thing about stuff in space is that once it gets accelerated, it doesn't decelerate very easily. It keeps going really, really, really fast. Here on Earth, you fire a bullet, yeah, it goes super fast, but eventually that bullet just, plunks down, gets pulled in by gravity, gets slowed down by friction, and it stops. Well, there ain't much friction up in space, and so these things can continue to accelerate or continue to maintain their speed, and once they have super amounts of speed, it can cause a lot of damage. Okay. Some debris in space will enter the atmosphere and will not totally burn up. When this occurs, it may land in populated areas, which could cause hazards for us. Some satellites or decommissioned space stations that re-enter the atmosphere have radioactive parts that we have to take care of, and they could contaminate a large area. And some of those parts that burn up, they don't always necessarily fall into the ocean. They could fall up into other areas. And if they do fall into the ocean, I don't know if you know this, but the oceans are really big. And so sometimes it's difficult to track down where they ended up. I'm going to include this video as well in your playlist. It's all about Canada's 50 years in space and the contributions we've made to what's gone on in space. I'm going to just really quick, I'm going to breeze through this, but one of the big ones to watch out for is the Canadarm, which is one of the mechanical structures that was included in the first space stations and the first modules that were sent into space. And it basically has helped construct the International Space Station and other devices that we have up in space. I'm not going to spend too much time talking about it right now. You can watch the videos to get that. We've also sent satellites into space. I know we talked about Anik 1 in 1972, which was one of the first communication satellites. Alouette 1 in 1962 was launched for non-military use, which was kind of interesting. And in 1973, we talked about it. We were the first nation to broadcast television via satellite signals, which I think is kind of cool. Have a run through and maybe pick a couple of these contributions to space that Canadians have had. Maybe pick out a couple of them and say, hey, we did this and we did that. I think that would be really cool. I'm trying to wrap things up. And then I want to just really quickly talk about issues related to space exploration. Should money be spent to explore space, or should it be used to fix problems here on Earth? I'm going to leave that question with you to sort of think about. It's a tough one to answer. Should we spend billions of dollars to go explore space? What are the potential pros and cons of this? What's the value of what we could find in space? What are some of the considerations that we might have politically, ethically, environmentally with spending so much money on space and space exploration? We've already talked about the fact that when we do stuff in space, we get a benefit from that because there's a lot of devices and a lot of technology that we use now commonly that we wouldn't have had if it weren't for space research and space exploration. So these are questions to consider. I'm not going to give you the answer to them because they're something you have to discuss from your own perspective and your own worldview. So I'm going to let you read through these in your notes on your own, but these are some of the considerations of the pros and cons of space. Some of the considerations of the things that we could find in space that's valuable to us. Things like, and it's not even listed on here, things like fuel, large amounts of hydrogen, other things that might be valuable to us, maybe even metals that could be mined on other planets. All of that stuff is potentially valuable for us. And then this is something I'll have you guys look at as well. These are political, ethical, and environmental issues associated with space. Some questions for you to consider. Who owns space? Is it the person who's up there at that point? Who owns the moon if we get there? Or what are the ethical considerations? Is it right to spend so much money on space instead of fixing problems here on Earth? Who's responsible for protecting space, the space environments from alteration once we get up there? So there's lots of things for us to consider as we move forward. All right, ladies and gentlemen, that is it. I am done teaching you Science 9. Well, I'm not done teaching you Science 9. This is the last video lesson. This is the end of the last video lesson. Thank you for sticking it through. Please don't forget that we've got some practice work you can be doing for this particular concept. I'm going to add to this this video resources list for you guys to give you a little bit more stuff to work off of. And other than that, if you guys have any questions, please track me down, fire me an email, pop on for one of my office hours, do your practice quiz, wait for feedback, do the summative quiz, and then you are done Science 9. High five to all of you for making it through. Stay safe, stay healthy, stay in touch with me. If you ever need anything, track me down. And hey, I hope we talk soon.